whether there might be some way of using Monte Carlo techniques in spinforms. And this is very tentative. It's also something very recent. But let me start with just a very flashy introduction of spinform quantum gravity. So spinforms have the aim of being a non-perturbative path integral of geometries. And to define them, you introduce a discretization, a two-complex, which is often dual to a triangulation. Then you build your quantum spacetime from quantum geometric building blocks that are derived from a constrained topological field theory, and the area spectrum of your triangles is discrete. And the physical content of the theory are transition amplitudes, where a single building block is like related to discrete gravity, and we have actual quantum amplitudes. They are not Vic-rotated, which is then, of course, the pain that we have to overcome when we want to use Monte Carlo. And in the short pitch, they are derived from GR. They don't make a reference to background geometries. And eventually, we aim of implementing diffeomorphism symmetry. However, and now the pitch is over, when you want to work with spinforms, you have to work with this partition function. And there are several computational challenges you have to overcome. One of them is this piece, the vertex amplitude, which I tried to symbolize here as this literal gluing of fuzzy tetrahedra into a four-simplex, and where this is an explicit contraction of, in this case, 5 tensors to give you a number, which can get very costly very quickly. That's one obstacle, and the other one is the sum here at the front, namely the sum over irreducible representations and intertwiners, where the representations tell you the size of the areas of your triangles. So you can imagine if you have a large triangulation, you have many triangles, you will have many, many variables to sum over, which is numerically difficult, and it screams for Monte Carlo methods, because that's one of the best ways we have to deal with many, many variables. However, our amplitudes are not positive semi-definite, and they oscillate. So you cannot straightforwardly apply Monte Carlo importance sampling by interpreting this partition function as your probability distribution. Nevertheless, in recent years, there has been a lot of numerical progress. Addressing the first issue, I would particularly like to mention this SL2C foam package, which is there to compute the spinform amplitude, the vertex amplitude for the EPLFK model. And we are, with my group in Jena, we are working on doing that for SE2BF theory for building larger triangulations. From a physical point of view, I think there has been a lot of insight, a lot of things learned from semi-classical insight, where I particularly want to highlight the effective spinform models that probably Hal Haggard and Seth Asante will talk more about during this conference. And Bianca also mentioned these acceleration operators for series convergence, which address this first issue about the sum over representations. Strongly related to these effective spinforms are what I call the hybrid representation that we worked on and that we'll explain a bit later, and these complex critical points. Monte Carlo methods have also been dabbled with, for example, using Lefschetz symbols and random sampling. And today I want to present an idea of doing importance sampling for these spinforms. So this would come from the semi-classical properties of spinforms. So if you have, for example, a single vertex, we know that this single vertex has critical points. So there are certain configurations which dominate in the limit that all representations, so the building block becomes large. And these would be represented by using coherent boundary states. The critical points of spinforms, which is a very generic result, come in basically two different forms. You have geometric force simplices that oscillate with the Regge action, and so-called vector geometries. If you go away from these critical points, you have an exponential suppression, which I tried to show here for SE2BF in explicit calculation. So this is like the absolute value of the spinform amplitude for an equilateral Euclidean force simplex, and at the top you have the oscillations of the critical point, and then if you go away from that, you get stronger and stronger exponential suppression. So what can we learn from this for larger triangulations? Because this is just a single force simplex, but you want to build your space-time from many building blocks. So typically, if you have two vertices, you would glue them together in the partition function by summing, and this is all what I'm saying to say for SU2. You would sum over the intertwiners, basically the quantum shapes that these tetrahedra that are shared between force simplices can take. So we can go back and reintroduce the explicit SU2 integrations over the several copies of representations, and introduce now the coherent states that I mentioned before. This is just a resolution of the identity. It's an over-complete basis that you can introduce, with the caveat that you now have this integral over coherent states. And we can do this trick again by introducing yet another object in between, which we call the gluing constraints. But this is a different representation of the spin-form partition function, where now each vertex comes with its own set of coherent data, for which you can at least heuristically apply the same logic that these should have critical points, and away from those critical points you should get exponential suppression. And we call these guys gluing constraints because they interpolate between the tetrahedra basically on both sides, and this is the so-called hybrid representation that we developed in my group. What are now the properties of these gluing constraints? They are actually peaked on having the two tetrahedra on both sides match. So this is the absolute value of these gluing constraints. They look fairly Gaussian and become more and more peaked the larger the representations become. So you can interpret basically this in this representation that you will get so-called, you will have the possibility of non-matching semi-classical vertices, which you can understand if they are non-matching as a non-metricity or torsion degrees of freedom being present in this partition function. And for the perspective now of using Monte Carlo methods, we now could expect that the major contribution to our path integral should come from matching critical points. And this is basically the idea that I want to put forward, that I would like to define a probability distribution for the intertwiners from the coherent states that are associated with those critical points. More precisely, I would take the absolute value of the change of basis from the coherent to the orthonormal intertwiner basis. Yeah, so the idea is simply sample these intertwiner degrees of freedom from those coherent states. And is there a way that we can test this probability distribution with an example that is well under control? And this example is, again, this equilateral force simplex for SU2BF theory. So typically, this calculation, if you want to do exactly, you have to sum basically over 2j plus 1 to the power 5 summons. So this, you know this will escalate very quickly. If all the j's are 1/2, this can be done on a computer in milliseconds. If the spins are 30, it takes 13 hours on a cluster. So it escalates very quickly, and it uses much more memory. So this is the orange points are the actual results that we did up to spins 40, which was very painful, compared to the semi-classical result in blue. And you see that the semi-classical result approximates the actual one better and better. And in comparison, I basically used the coherent states then as a probability distribution for a Monte Carlo algorithm, and did the simulations for 10 runs up to 10 to the 6 samples, and it is, as you can see here, extremely close to the full results with rather small error bars. So these simulations are not enough to fully show how big the error bars are, but this is already very encouraging, in particular because I'm doing much less calculations. I was able to produce these results in 1 week rather than, and not by totally straining the cluster. And I was able, which wasn't possible for the full algorithm, to push this to even spins 80, and I even tested further up to 120 and more. So it is actually very surprising for me how good and fast this agreement of those results are, and how fast the convergence is. In comparison, I also tried random sampling for these results, and I wasn't even getting to the correct order of magnitude of these results. So I'm surprised at how good this agreement is, but as I said, the amplitudes are oscillating, and the sign problem is also present there. The sign problem is hidden in if you would want to define the global phase of the amplitude. So that is something that is very difficult, and that only slowly converges. So, okay, that's great timing, because then I basically want to come to the summary and conclusion. So I wanted to convince you today that there might be parts of the spin-form partition function to which you can apply Monte Carlo techniques. In particular, I wanted to do Monte Carlo importance sampling for the intertwined degrees of freedom from those critical points. So the idea is that if you get exponential suppression away from the critical points, and you can decompose your partition function into individual vertices, the idea is then to sample intertwiners with respect to these critical points, and the first tests are extremely encouraging and very, very nice. However, of course, one has to test this now for larger triangulations, where in particular the question of convergence arises, and I haven't addressed the spin labels themselves. So that is something that would have to come first. But I would say that before one tries to go to the full models, it's better to first start with simplified models and try to make them work, because already there you quickly run, in particular for the spectral dimension work that I did with my student Alexander and Johannes Thüringen, who was talking at the same time in the other session. We quickly ran into these issues just from summing over a few variables. So we are in desperate need of better methods, but we are getting there. So we are working on turning spinforms into a computational formalism, and what I want to do is actually try to measure the sign problem and estimate the potential of Monte Carlo methods for spinforms. With that, stay tuned for the future, and thank you for your attention.
Thank you, Sebastian, for being on time. First question, Marco?
Yeah, I didn't understand this part, that these gluing conditions that you introduce. Don't they change the physics of the model? I mean, this is like a boundary condition in between two simplices.
All these transformations are just introducing resolution of the identity. At the level of SU2, this is all fine.
So it's like a unit.
It's yeah.
But why do you introduce it? I mean, why? What does it do if
yeah,
it doesn't change?
So my initial plan for this was to actually utilize the semi-classical formula directly in order to being able to avoid computing the vertex amplitude in full detail. However, what happens is that essentially the quantum corrections that you get in spinforms remain non-local because it is a gauge theory. You can't just chop it up into different amplitudes. You get the wrong scaling behavior. So that is a bit of an issue. So I had an idea, that's why we developed this method, but it still teaches you something about what the different configurations are and how relevant, or how to interpret the spinform models. And I think it also gave support, or is a different way of getting to these effective spinform models.
Okay, thank you.
Pass to Bianca, last question.
Yeah, thanks, Sebastian, for this nice talk. You mentioned the sign problem when you discussed summing over intertwiners and the global phase. Can you elaborate on that? Where the sign problem appears?
Yeah, so when you run the simulations, you get a complex result. And there's like, from the actual result, you can compute the phase for like spins 1, and you can extrapolate it to higher orders. If you do the full calculation, then you see that you get a real part and a tiny imaginary part. Here, this imaginary part doesn't get tiny. It's just 2 orders of magnitude smaller than the real part. And there, I would probably have to put much more iterations into